All right, welcome back, you guys. We'll take a look at continuity today. With continuity, what you want to remember is there's no holes, no gaps, or jumps. Okay, let's talk about no holes for a minute. So technically, that means that FFC is defined everywhere. If there's no holes, let me give you a picture of that. Here's a bad example of a hole. All right, we can't have this. Can't have this. Not allowed. Right? No holes, jumps, or gaps. Another way to think about this, you may have learned this in high school. They say, hey, you have to be able to, if it's continuous function, you got to be able to draw it without lifting your pencil. Right? Well, you got to lift your pencil if you're drawing a hole. Right? Second thing is the limit has to exist. So number one, FFC's got to be defined. Number two, the limit's got to exist as well. So this is saying no gaps. Let me give you a picture of no gaps. Like, for example, if you got the function coming along, the limit approaches that, but then it has this gap, right? So no gaps are allowed, right? That's not continuous in red there. So the limit's got to exist. So number one, FFC's got to be defined, no holes. Number two, the limit as x approaches c of f of x has to exist, so you can't have a gap. And not only do those two have to be achieved, but number three, the limit as x goes to c of the function must equal f of c. Must equal f of c. So in other words, no jumps either. Like this would be an example of that. Can't have that going on, right? That would not be continuous either. We know the limit exists, but again, the limit has to equal the actual functional value. So you can't have a hole, you can't have a gap, you can't have a jump if you're really a continuous function. And this last scenario, this is referred to as a removable. This is a removable discontinuity. I have another picture of it down here as well. A removable discontinuity means if I plug it back in right there, and fill it in, now it's continuous, right? So that's a removable discontinuity. I can plug it in and it'll be fine. A non-removable, there's no way I can make that continuous, right? With just replacing of a point, right? So that's a non-removable discontinuity. Gap is a good example of a non-removable discontinuity. This first one up here in blue that I did, this is also that's a removable, right? I could just fill that in and then it'd be fine, right? So that's a removable. Let's look at this one. So where is this thing discontinuous, first of all? And hopefully you say anywhere where you have a hole, jump, or a gap, right? So at -2, right? Because I got this vertical asymptote, that's a problem. And at 0, good. I've got the gap there at 0, see the big gap? Also at 2, I've got the hole. And finally at 4, good. That's where I'm discontinuous. Now, which of these are removable? In other words, you can replace it if you will. Good. 2. So that's the removable discontinuity. All the other ones are non-removable. There's nothing you could do with the asymptote. There's nothing you could do with the gap. You've got a problem there with another asymptote there, right? So nothing you can do. Those are non-removable. All right, let's talk about f of x equals 3 minus x to the 1/5. And we describe a set of x values where the function is continuous and using interval notation. So the real question is, do we have any problem childs with this, right? Is there anything that causes us to like a divide by 0, or can we not take a fifth root of a value? Those are the kind of questions that I'm thinking about when I'm thinking about the fifth root of 3 minus x. Well, Can you take a fifth root of like a negative number? Yeah, you could do that. That's okay. You can take an odd root. Remember, negative 2 to the fifth is negative 32, right? Negative 2 times negative 2 times negative 2 times negative 2. Did I say that 5 times? So the fifth root of negative 32 is negative 2. So yeah, you can take an odd root of a negative number. So this is going to have, your radicand here is not going to have any restrictions. So your domain is just going to be all real numbers, right? In other words, from negative infinity to positive infinity is the set where it's continuous. It's continuous on the entire domain there. Okay. Whereas the square root, the one down below there, that's square root of 6x minus 35. Well, this is the second root. This is an even root. Can we take a square root of a negative number? No, because there's, right, the square root of negative 9 equals negative 3. No, that doesn't work because negative 9 does not equal negative 3 squared, right? That doesn't work technically. So, in other words, this stuff has to be greater than or equal to 0, right? That's your domain on this, and that's also where this thing is continuous, right? So we're going to solve that, add 35 to both sides, divide by 6, and we're dividing by a positive number, so we don't need to switch the sense of the inequality there, right? That's which way it goes, so we're okay. So x is just greater than or equal to 35 over 6. So that's where we're continuous. This function is continuous from 35, 6 on. In other words, that's kind of what that function looks like, right? That square root function takes off there from 35, 6. So, all right, if I'm taking a look at this next one here, where's this thing continuous? So first thing I'm thinking is, well, I can't divide by 0, right? Is there anything that causes this to be 0? X squared plus 1. Yeah, he's right. There's nothing, right? Because if I square that, this is always positive. And then if I add 1, I'm still positive. So anything I plug in for x, it doesn't matter. Positives, negatives, zeros, fractions, whatever it may be, I'm always going to have a positive number on the bottom. So I have no restrictions here, actually. So we just say, hey, this thing's continuous on the whole domain again. Negative infinity, positive infinity. I don't have any issues with that. But once we start getting into some trig down here, tangent of x, now we're going to have a little bit more to think about here. So let's go ahead and write function here. Let's go ahead and write this in terms of sine and cosine. So I've got f of x equals sine over cosine, and then this is all over that x squared plus 1. So keep change flip, multiplied by 1 over x squared plus 1. And I'm looking at that x squared plus 1. I'm like, okay, the x squared plus 1 again is fine, right? That thing is always going to be positive, so I have no restrictions on that. But I do have an issue here with cosine. Remember, we can't divide by 0, right? So anywhere where the cosine is 0, this is a problem, right? We cannot have that be 0. We cannot divide by 0. So then I'm just thinking to myself, okay, well, the cosine of what is 0? Right, you're looking on your unit circle and you're like, oh yeah, pi halves, cosine of pi halves is 0. All right, cosine of pi halves is 0. I know the cosine of 3 pi halves is also 0, right? The cosine there is also 0. So I start listing. I'm like, I know that one's 0. So pi halves, x being pi halves is an issue. 3 pi halves. I could go around again and back to the pi halves. So like 5 pi halves, right? Dot, dot, dot. I keep going. Same thing in the negative direction. If I go negative pi halves, the cosine's also 0, right? Or negative 3 pi halves, which is coterminal to pi halves. Or negative 5 pi halves. Anyway, so on, right? So I have an infinite amount of locations where the cosine is 0, right? So how could I sum these up and make it nicely done? Well, hopefully you can kind of see this pattern here. What's changing? I have a 1, 3, 5. I'm not going to worry about the negatives for a minute, but I do have those negatives, -1, -3, -5, right? Can I write this in a pattern? I need this to change 2n plus 1 pi over 2. The pi over 2 stays stable on this, and your n is just the set of all integers. N is an element of the integer. So let's plug it in. Like, for example, you know, the integers, remember the integers are so if I plug 0 in, 2 times 0 is 0, 0 plus 1 is 1, so there's the 1 pi halves. If I plug 1 in, right, so that this one gives me the pi halves. If I plug 1 in, I get 2 times 1, 2 plus 1, 3 pi halves. That gives me the 3 pi halves. I plug 2 in, that'll give me the 5 pi halves, right? Now let's go with -1. If I plug -1 in for n, I got 2 times -1, -2 minus 1, -1 pi halves. If I plug the -2 in, -3 pi halves, and so on. See how this one will knock them all out for me? You could also say, so this is the best way to say it as far as with the integers there. So that's where it's not continuous, right? So we're going to say the set of all x values x. So let's do it in set notation. X such that I can be anything, any real number, except for I cannot be 2n plus 1 pi over 2, where n is an integer. So I can be anything but those, right? Because that causes the cosine to be 0. That's the problem with that. You could also say n pi over 2, where n is odd. But you really should be a little more specific on that, because you want to include the negatives there, which I did. All right, let's keep going here with cosecant 4x. I'm thinking about this as 4 times 1 over sine of 4x. So we got 4 over the sine of 4x. This is my function. And again, we can't divide by 0, so I'm just thinking to myself, where is this not defined? Well, anywhere where this occurs, right? If my denominator is 0, I have an issue here. So now I'm just thinking to myself, well, if I'm looking on my unit circle, I know the sine of pi is 0, right? I know the sine of 2 pi is 0. I know the sine of 0, I should have started with 0 at that one. Sine of 0 is 0. Right, sine of 0, 0, sine of pi is 0, sine of 2 pi, and so on is 0. I could go negative pi, and so on, right? So, I got to do this in terms of x. So when does, 4x equal those, right? Well, I have 0 pi, 2 pi. So I have that being, or negative pi, -2 pi. So let me just sum that up. That'll be n pi when n is an integer, right? N could be 0, 1, 2, 3, or -1, -2, -3, and so on. So what I'm going to do is I'm going to say 4x equals n pi. When does 4x equal n pi? And then I'm going to divide both sides by 4. N pi over 4. Again, n is an integer. So where is this continuous? Well, everywhere except there. All reals except for n pi over 4, where n is an integer. All right, other than that, it'll be fine. Continuous. All right, let's keep going here. Now we've got this rational function. And if you remember with rational functions, if you factored this from your pre-calc course, and if you saw binomials canceling like this, or a set of factors canceling, then you had a hole right there. So you have a hole at x equals 3 on this function, right? And then if it doesn't cancel, so this actually behaves like the simplified version. But remember, this is a different function. It has a vertical asymptote. Oops. At -3, right? So let's get a little picture of this. I got this -3, oops, asymptote, and then at x equals 3, I've got a hole. 1, 2, 3. I've got a hole. I've also got a horizontal asymptote because the degree of the denominator is greater than the degree of the numerator. So I've got a hole, and it kind of looks like this. Of course, I could plug in some other points if you wanted to, but this is kind of what this thing looks like, right? If you want to get a picture of that, which is always nice. But where is this thing continuous? Well, it's continuous from -infinity up to that asymptote of -3, and then from -3 up until that hole at 3, and then it keeps going after the hole. All right, that's where it'd be continuous. Now, the only one that's a removable discontinuity is where? Yeah, the hole, exactly. So the hole, that's your actual removable discontinuity. The other one's a non-removable, right? Where the asymptote is non-removable. So I don't know. Did we really need the picture? Probably not, but nice to kind of look at that way. I would probably do most of my rational functions probably similarly. So this one down here, I would go ahead and factor that. Just make sure you don't have a hole. So I factor the bottom here, x and x. Looks like that'd have to be, let's see, factors of 15. One's got to be positive, one's got to be negative. I think plus 3 minus 5 should work. Make sure you FOIL that and check it. X squared minus 5x plus 3x minus 15. Sure enough, that's your x squared minus 2x minus 15 properly factored. So it does not look like we have a hole. Nothing cancels. So we just have two vertical asymptotes on this. So we're discontinuous at -3. And both of these are non-removable discontinuities, right? So if you were graphing this thing, you'd have -3, and then you'd graph whatever that thing, I don't know what this looks like. I'm just going to say it looks something like this, and then it's over here, and then again, who knows what this exactly looks like. What we care about is the continuity. Where is this thing continuous? From -infinity up until that first asymptote, from the -3 asymptote up until the 5 asymptote, you're fine, and then after 5, you're also fine. So you just have those breaks at your vertical asymptotes. All right, this last one we've got this piecewise defined function. So we're going to take a look at where this is continuous or not, and then classify them as well. So let's take a look at this x cubed minus 8. I'm going to go ahead and, if you remember, a cubed minus b cubed factors into a minus b, and a squared plus ab plus b squared. So in this case, I have x cubed minus 8 over x squared minus 4. So this would factor into the x cubed minus 2 cubed. So I'd have x minus 2 a squared plus x times 2, or 2x, plus b squared, so that's the 2 squared, so the 4 on the end. and the denominator factors into x minus 2x plus 2. So it looks like we have a hole there at 2. And then we're going to have a vertical asymptote at that negative 2. All right, if you're trying to get a picture of this thing. And, you know, where's the hole at? Well, if I look at the simplified version of this, I could find where the hole is at, because it behaves just like the simplified version. So I could plug the hole in. Let's see where that's at. 2 squared plus 2 times 2 plus 4 over 2 plus 2. So I got 4 plus 4 plus 4. So I got 12 over 4. So I got 3. So it looks like f of 2 is 3. But remember, that's just where the removable discontinuity is, right? Because I plugged it into the function that did not have a hole, right? That looks the same. But ideally, I'm plugging in some other points. Like I would plug in, you know, you throw in like 3, and you plug in, you get 3.8. By the way, I made a little note here. 4, I got 4.6. So just plug a few in, and you get a feel for this thing. Let's do some to the left of the hole. Remember, it's undefined here. That's where the hole is. But let's go left of that. So let's see. 0 would give us what, 2? Plug in negative 1. I get 3 on that. Negative 2 is the vertical asymptote. Let's see, negative 3 spit out negative 7. Negative 4 spit out negative 6. Kind of looks like this a little bit. Anyways, that's kind of what this thing looks like. All we care about is the continuity. It's not too much of a graphing lesson probably, but let's take a look at these last points. If x is 2, it's giving us the point 3. If x is 2, y is 3. Oh, they just filled that in. Now it's filled in. So it's defined there now. No problems there anymore, right? Because it just got filled in. And then if x is negative 2, y is 4. Negative 2, comma 4. So even that, so on the asymptote, now it's actually defined here, right? So then the question becomes, okay, well, where is it discontinuous? Well, it's discontinuous. We replaced that one, so that's not a problem anymore. What about the vertical asymptote? Is that still a problem? I'm pretty sure. Yeah, so even though it's good, so even though it's continuous, it's still a problem. I still have that gap of it because it's not continuous. Can I still draw without lifting my pencil? No, impossible. So still not continuous. So it's continuous everywhere except at that dang vertical asymptote still. Negative 2, right? This is where it's continuous. Everywhere except negative 2. Thanks so much for watching. See you next time.